So, well there and welcome back. So, you have started watching videos on mathematical foundation of robotics, and in the unit 2 we are discussing specifically on modeling different modeling techniques of humanoid robot or collaborative robot. In this context today we'll discuss about some introductory robot dynamics. Now, why dynamics is needed? Because you see, so far, whatever we have in our model, uh, we have these relations, right? So x equals to, this is 4 by 4 matrix, homogeneous coordinate transformation matrix, and theta we have 4 cross 1, and so this is kinematics based model which we have, and if you see structurally it has only captured robots link length. Okay, we'll come to this. Then also we have one relation we have deduced, Jacobian, in terms of Jacobian matrix. So differentiating this, you have got velocity relation also. Okay, and this is, you remember. Okay, so this is function of theta. Isn't it? You have got it. And this for redundant robot, so this actually inversion will be a pseudo inverse, and you know that we noted this as inverse, J inverse. This is a pseudo inverse of, again, function theta equals to actually J transpose, then J transpose, this inverse. Okay, and then what else you have? These are the relations which we have so far, right? And if using these we have exploiting this, we have resolved rate control. Somehow all these actually, especially for humanoid and collaborative robot, these modeling techniques somehow are good enough, so that your robot can follow a trajectory, okay, like this. So it can do pick and place operation, it can follow a particular trajectory, all kind of things it can do. But nevertheless, the modeling is incomplete, in the sense that when we are talking about robot, okay, say tooling robot, the length is always associated with some mass, isn't it? Huh? But we assume that links are massless, which is not correct. So this is actually we have a model which is far from the truth. Okay, so our robot dynamics intend to capture that completeness by actually incorporating mass in the model. And when we incorporate mass in the model, then we can see several other forces and torque will come into the model, and those models are more complete model than the model we have. So we study dynamics. So why we study? Why dynamics? I try to explain. Because we want to make our model a little bit more perfect. So why? Because then controlling will be easier. Say, if I know the dynamics of you as an individual, okay, your parents know much better, then they can control you better, because they know the dynamic behavior of you. Similarly, that is because this is more complete. So it is always means just logical example I am giving. It is always easy for parents to control their children rather than a teacher or somebody else who has limited interaction with you. Okay, so analogically, we are studying dynamics because we need to more complete model we need to create so that we will have more information about the robot, so that we can control robot in following a perfect trajectory. So if say resolved control is actually resolved control, so if this is your say perfect trajectory, if you follow resolved control, the trajectory could be something like this. Huh? Okay, so in collaborative and human and robot, normally we are satisfied with that. If you are, then yes, the resolved control together with forward kinematics, inverse kinematics will do your job. But if you are not satisfied with that, means I need a stringent trajectory. I need my robot to follow stringently this trajectory, then definitely we need a more complete model. That's why we are going to study dynamics. But again, it's a huge field, and books has been written on dynamics. It's a multi-body system, and there will be so many coupling forces coming into the picture. So that makes model more complex. And also, even in dynamics, we ignore something. What are those things? For example, joint friction. Okay, we ignore. Then other environmental uncertainties, manufacturing uncertainties, and thereby manufacturing defects. Those are not there in the model. But even then, dynamics definitely helps you to create more perfect model. So let us stay tuned and then fasten your seatbelt and let us study dynamics. But this lecture will be confined only to the introductory level. Okay, so again we will consider tooling robot manipulator. And in dynamics, what our intention, we need to create a relation between cause and effect. So in robotic sense, suppose I have a manipulator and here I have a motor, here I have another motor. So this is hypothetical, right? Because in actual robot, the motors are actually kept somewhere else, and then through transmission at a very convenient place it remains, so that motor is heavy, and we do not want to actually invite more problem by hanging a mass over here, and with that motor robot will move. So if possible, so those are design issues which we are not trying to address here. But here we are trying to, what I am trying to tell you, that if this is a motor, it can create a torque. This motor is creating another torque at the joint. Okay, so motor can be anywhere, but torque will be generated at the joint. And this torque will create some motion. If you energize motor, for example, I am energizing my muscles and my hand is moving. Similar is the concept. So we are trying to create a relation between cause and effect. If the cause is the motor torque, then effect is motion. Okay. So all this we will study, and so this is actually in a very simple way we will study dynamics, dynamic model of a two-link robot manipulator. Now, there are two very popular tools for making dynamic model. One is known as Newton Euler method, another Lagrangian method. Okay. So both the methods are based on Newton's second law, but since Newton's second law is confined to physics and where it's confined to particle dynamics, and we are talking about a multi-body structure here. So Newton-Euler, which is based on Newton's law, Lagrangian method, which is again follow Newton's law. Okay, so these principles are derived. Okay, so Newton-Euler's method, either of this you can actually use. Newton-Euler method computationally less complex, but you need to create free body diagram before writing the equation for force and motion. Okay, and if you make any mistake, so it's a error prone. If you make any mistake in drawing free body diagram, that means you have forgotten to consider some force or something like that, then the model will be erroneous, right? So, but it has computational advantage compared to Lagrangian method. So here both the active force and reactive force need to be considered correctly. On the other hand, in Lagrangian method, based on energy of the system. By the way, they are very, very general method. They not only they can be used for dynamic model of robot, but any multi-body system dynamics can be studied using these two tools. Okay, so they are very powerful. So based on energy method. Okay, and computationally it is more complex than Newton-Euler method. However, since this is straightforward, okay, and today we have computational muscle power, so we will study Lagrangian method. Okay, so let us see how using Lagrangian method we can we will exploit Lagrangian method to derive the dynamic equation for a two-link robot manipulator. Okay. So first of all, we need to have a coordinate frame because we are talking about calculating energy, and potential energy requires a coordinate frame. Okay, so we will consider a coordinate frame like this, and let us consider again a two-link robot manipulator. Okay, having length L1, having length L2, and let us consider mass of the link L1 is confined lump mass. Okay, confined here. Okay, and this is say M1, where mass we are considering is a lumped mass and it is situated at one end. You can also consider the mass is actually lumped mass is concentrated at center of mass. Then you need to have a, say if I consider here lumped mass, then I need to have this information that how far from one end the mass is. Say if you call it L1, then that will also be okay. Okay, but here in this particular model, but they hardly make any difference. Okay, so we are considering lumped mass at the end. Okay, but you can argue, okay, this is not a lumped mass, right? Robot is actually a structure like this, so it will have a kind of is a 3D structure. Yes, it is, and mass can vary. Yeah? So all this will invite additional complexity which is not in the robotics domain. Okay, and you can use very well today. You have finite element packages. They can consider mass which is distributed along the length. Okay, but they will invite additional complexity and produce very significantly negligible superior result. So with this assumption, logical assumption, we can achieve simplicity, and after all you need to know the principle, and then of course you can use packages for when lumped mass can be a distributed mass. Is it clear? I think, right? So now let us consider coordinate frame, planar, 2D planar, very simple tooling robot manipulator we are considering for developing dynamic model, and masses are situated at the end. Okay. Now Lagrangian equation needs to be understood. Okay, and this equation we are not deriving, we will use them. What is Lagrangian equation? You see, we have to consider a function, Lagrangian function L. Let L be the Lagrangian function which is defined as L equals to system's kinetic energy minus system's potential energy. And once you have that Lagrangian function, then let us also consider theta I, generalized coordinate of the system. Generalized coordinate of the system. Okay. So if you generalize system means this is theta 1, say this is again theta 2. So these are known as generalized coordinate. If it is 6 link, then theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. So theta I will be equal to I equal to 1 to 6. Here I equals to 1 and 2. These are called generalized coordinate. As I told, Lagrangian equation, Lagrangian dynamics is used for many other fields. So we represent Lagrangian equation in this form. Then the equation is telling this: if you do this, okay, what is this? If you partially differentiate with the derivative component of the generalized coordinate, the Lagrangian function, and then again differentiate it with respect to time, minus if you differentiate that Lagrangian function with respect to generalized coordinate, then this will give you the cos tau, that is the torque. Okay. So this left hand side, they are the motion parameter. Okay, we will see, and this is the relation between cos, this is cos and this is effect. Cause and effect relation you can get by Lagrangian equation. This equation we have not derived but can be derived. We will use it. Okay, but understanding it very important. So L is Lagrangian function and theta I is the generalized coordinate. So what we need to do first? First we need to create step 1. Create Lagrangian function. Lagrangian function L. So for creating L, what you need? You need to calculate system's kinetic energy and you need to calculate system potential energy. So we'll have to do. And then you see, so step 2, to calculate Lagrangian function, you need to first calculate kinetic energy of the system. And step 3, need to calculate potential energy of the system. Then step 4, calculate, once you have L, okay, create Lagrangian function. So you need to so calculate L equals to Ke minus P, and then calculate partial derivative of this function with respect to theta I dot. Okay. So you need to calculate theta I dot. Okay. That means you need to differentiate with respect to. So you need to just figure out partial differentiation with respect to theta I dot. Okay. Because you will be having theta I dot, theta, all kind of thing in this function. So you calculate that easily. And then step 6. So step by step we will do all this. So calculate ddt of del L del I this. Then step 7, calculate del L del theta I. So when we have all the materials, we collect them and put them in this equation and we'll be able to get system dynamic equation. Very, very powerful, okay? So we'll do that. Now, you see, first I need to calculate. That's why you see I have drawn this tooling manipulator in this peculiar form, not like this. This way you can also do, but this is more convenient and it will make my computation a little bit easier, means simpler. That's why we are, these are all the same, right? So here then gravity force will be coming into the picture. Gravity's direction is this, okay? It is negative y-axis direction gravity is acting, okay? And we need to have this frame, otherwise we cannot calculate system's potential energy, okay? So slowly we'll follow these steps and we'll end up in deriving dynamic equation of this tooling manipulator, okay? So this is our main objective. So let us proceed. So we are quickly redrawing. So this is your x, this is y, and this is my robot, tooling robot, otherwise it will be too complex, too complexity will be there. But today, there is a revolution in modeling technique also, because you have MATLAB Simulink or Octave Simulink like a tool. You can just symbolic computation tool also you have. So using symbolic computation tool, you can actually model any multibody system. They are easy. So this is your theta 2. Okay. So m1, m2, theta 1, theta 2, and gravity is acting in this direction. So kinetic energy of link 1. First of all, kinetic energy of link 1. So this one, this is equals to, say, K1 equals to half m1 L1 theta 1 dot square, half mv square v equal to omega r. So omega is actually, that physics formula, omega equal to theta dot. So this is as simple as this. We call it. Now kinetic energy of link 2. Say this is K2. Now, for calculating kinetic energy for this link, what you need? You need also that half m to half m2 L2 v squared. Now v will be a velocity which you do not know, and we need to figure out. Okay, for figuring out, for calculating K2, we need actually again this to be resolved like this. Say x2 equals to L1 sin theta 1 plus L2 sin theta 1 plus theta 2, and this is actually assuming S1, this is S12. You know all this. So x2 in a compact form will be L1 S1 plus L2 S12. Similarly, y2 will be y2. So we will resolve, okay, because we need to calculate the velocity at this point. Okay, point 2, v2. Okay, for that we need all this information. So minus L1 cos theta 1 minus L2 cos theta 1 plus theta 2. Okay, let us call it. Now differentiating one, what we get is this. X2 dot equals to L1 cos theta 1 plus L2 plus L2 cos theta 1 plus theta 2, theta 1 dot plus theta 2 dot. Okay, you can, with a notebook, you can do with me. That will be very good and increase your confidence. Okay, L1, and if I make any mistake, you will be able to correct me. That is another advantage. Differentiating this with respect, so you are getting L2 sin theta 1 plus theta 2, theta 1 dot plus theta 2 dot. Okay. Now we need to calculate V velocity at this point, right? So since v2 squared equals to x2 square plus y2 square, we get from 2 what we get? L1 square theta 1 dot square plus L2 square theta 1 dot square plus theta 2 dot square plus twice theta 1 dot theta 2 dot plus twice L1 L2 plus theta 2 dot 2 cos theta 1 plus theta 2 plus sin theta 1 into sin theta 1 plus theta 2. So this you will get, okay. So what we are doing here is very simple, right? I am squaring it. So this a plus b, this is a, this is b, a plus b whole square. Then I am also squaring this. This is a, this is b, you can assume, so a plus b whole square, as simple as this. And then squaring them and adding them together, a little small algebra, okay, 12 plus math, and you will get this. Please check, there is no mistake, okay. So this will be further can be simplified in this form, L1 square L1 square plus L2 square plus twice theta 1 plus twice L1 L2 cos theta 2. So this we have made like this, theta 1 dot square plus theta 1 dot theta 2 dot, okay. So once we have v2 velocity, then kinetic energy k2, then kinetic energy of this link k2 will be equals to half m2 v2 square. So k2 will be equal to half m2 L1 square theta 1 dot square, okay, plus half m2 L2 square theta 1 dot square plus theta 2 dot square plus twice theta 1 dot theta 2 dot, okay, plus m2 L1 L2 cos theta 2 times theta 1 dot square plus theta 1 dot theta 2 dot, okay. So this is the expression for kinetic energy of link 2. It's a little bit complicated, isn't it? So we'll have to see we'll have to see that how we can manage so many expressions, and we will try to work on this we will continue our discussion in the next class. And then we also I appreciate if you bring copy and work with me so that we together can deduce the dynamic equation for a robot manipulator. That will build up your confidence to understand what is going on. Until then, I wish you all the best. Stay safe. Have a nice day. Bye-bye.